In this video, we're going to have a look at esters. Esters are produced from the reaction between a carboxylic acid and an alcohol, and it helps if you consider this when you are looking at the structure and therefore naming an ester. There are two structural features of the name of an ester. The first part, the alkyl part, comes from the alkyl chain that is attached directly to an oxygen atom. So that's derived from an alcohol. And the alkanoate part of the name comes from the part of the structure which is attached to the carbonyl, and that comes from the carboxylic acid. If we have a look at this structure here, the first thing that we want to do when naming it is identify the oxygen that is bonded directly to an alkyl chain here. So if we have a look at that, we can see we've got 1, 2, 3, 4, 5 carbons. So the alkyl part becomes pentyl, 10 for the 5 carbons. The next part is we look at the component of the structure attached to the carbonyl, and in this case we see that we have 2 carbons, so it has the prefix of F, so it'll be F and O8. So we've got pentyl F and O8. It's important to keep in mind that esters can be drawn in both directions, so you can't decide which alkyl group is the alkyl or the alkanoate part of the structure purely by what's on the left or right. So every time it's very important that you firstly identify the oxygen that is bonded to an alkyl group. So in this case it is on the left. So we can see that has got 2 carbons. So in this case we've got ethyl. Then we have a look at the part of the structure attached to the carbonyl, and in this case we can see we've got 1, 2, 3, 4 carbons, so that's going to have the prefix of bute, so ethyl, bute and O8. As stated before, esters are formed by the reaction of a carboxylic acid with an alcohol under the right conditions. In a laboratory, those conditions are concentrated sulfuric acid, which acts as a catalyst to speed up the reaction, and reflux conditions, which allows the reaction mixture to be heated for an extended period of time without losing any of the reactant or product vapours due to evaporation. During this process, water is also formed. So what happens is we take an OH from here and a H from here, and that's going to give us our water. If we go back to our original structure, we can see we've now got this component that comes from our carboxylic acid and this component that comes from our alcohol. So essentially a new bond forms between those two things once our water has been removed. So we end up with over here from our carboxylic acid, that now bonds to the oxygen from our alcohol, and we end up with our ester structure. A few things to take note of. Firstly, you'll notice that the reaction is reversible. What that means is not all of our reactants are converted to products, and the reaction mixture will combine a mix of all 4 of the reactants and products. So the reactant mixture will have your carboxylic acid, your alcohol, your ester and your water. So if you're trying to produce just an ester, further steps of purification will be required to isolate that ester by itself. Just to note again that the concentrated sulfuric acid that is used acts as a catalyst, and that increases the rate of reaction so it occurs in a reasonable time period. Now, reflux means to heat for an extended period. So the heat acts in a similar way to the catalyst. We heat so that we can increase the rate of reaction. However, under reflux, because we're heating for an extended period of time, the reflux apparatus is required. So the reflux apparatus, you can see over here, consists of a pear-shaped round bottom flask and our water condenser. This allows the extended heating without loss of reactants or products. You can see we've got water coming in the bottom and out the top. That means keeps the condenser cool. So as our vapours travel up and come into contact with the cool surface of the condenser, they condense back into a liquid and return to the reaction flask. So ultimately we're preventing the escape of vapours of either the reactants and the products, which will help increase our yield. Just as esters are produced by joining a carboxylic acid and alcohol together, an ester can be broken down into those components via a process called hydrolysis. And hydrolysis basically is the addition of H2O. Having said that, hydrolysis can actually occur in two situations. One of those being alkaline conditions, and that is where we're adding a hydroxide ion as opposed to a water molecule. So we've got one less hydrogen in that situation. When we've got hydrolysis and we're adding a H2O molecule, essentially we can think of the H2O as an OH and an H. We're going to attach the OH to our carbon. It's going to give us a carbonyl, and that hydrogen will attach to the oxygen. And you can see there that our ester has been split back into a carboxylic acid and an alcohol. It's important to take note that this requires certain conditions to occur. So those conditions are reflux and an acidic environment. So if you're writing an equation for this, you would see reversible reactions, H plus to show it's an acidic environment, and reflux to show it needs to be heated for an extended period of time. Under basic conditions, we can think of our hydroxide ion as an O and an H. The oxygen is going to attach to the carbon and the hydrogen to the oxygen over here. So you can see in this situation we've ended up with a carboxylic ion instead of a carboxylic acid. So due to the presence of one less hydrogen, our carboxyl group here is one hydrogen short, meaning it's actually a carboxylic ion rather than a carboxyl. So for the hydrolysis of esters, if we've got an acidic environment, we're going to get a carboxylic acid and an alcohol. If we've got an alkaline environment, we're going to get a carboxylic ion and an alcohol. It's worth noting also that in this situation, if